So that's the terms in E1 direction. Now we get F2. That will be the terms that are in 2 of t plus this term over here, which is omega 1, 2 with a factor of F1. And so that's the parts in F2. And then we get a third part, which is the elements which are going into the third direction. So that will be a F1 of t times omega 1, 3. Plus F2 t times omega 2, 3 c of t. So from this calculation, you in particular see like your justification of this statement over here. What I said is that the derivative will usually not be tangent to S, because usually there's no reason why this expression over here should be 0. So maybe for some functions, F1 and F2, that might be the case, but like usually there's no reason why this sum here should be 0. So now let's have a look at both of these terms. The one that is tangent, so that's this part, which is the tangent part, and then we have this part, which is the normal part. So for the tangent part, well, like it's a formula, but there's not much that we can do to simplify that further. And usually, if you have like a complicated expression that is intuitively something interesting, maybe in this case it's the tangent part of the derivative, then usually it's a good idea to give it some name. So to just abstract it away, and that's like the definition. So let E1, E2, and E1 be a frame, and x of t, then f of t, E1 of c of t plus f2 of t, E2 c of t, be a vector field along the curve C. Then, and now it's called the covariant derivative. Covariant derivative of x is the vector field along C, defined by essentially by these two equations up there. So we'll continue over here. it's so the denotation, like the way it is denoted, it's by this symbol. So it's a bit of a strange-looking symbol. This nabla is standing for this covariant derivative. So that's why you have like covariant that's like somehow indicated by this nabla. And then you remember that it's a derivative. But really you should think of all of that together as a name. So this one is the name. So it's like, you could have also called this guy like y, but it's usually denoted by a ddt with the nabla of x. But this one is a vector field along a curve, and it has, again, components along E1 and E2, and these ones are given exactly as in the formula up there by these formulas of 2. 1, 2. E1 plus so you should read of that as, again, evaluated as for every t in here as well. So really, this is the name of the vector field, and that's the definition. So the observation here is that this expression over here only depends on omega 1, 2 and omega 1, 2, 1, which is just minus of omega 1, 2. So it really depends only on omega 1, 2, which is the intrinsic part of the connection. Omega 2, so it's intrinsic. So if you don't like the word covariant derivative, you can also think of that as the intrinsic derivative. The thing that like ants living on the surface, if they see like a vector field along a curve, how can they measure like these vectors, how they change? Well, they can't jump in the normal direction, so they can't measure the normal changes, but they only will measure some change of the vectors, and that gives them a vector field again, and this one is denoted by ddt. So that's exactly like the intrinsic change of we will, in a second, we will see a little bit more properties of this covariant derivative, but let's return to the normal part. So we still have this part over here. So that's the first step was the tangent part. So from the normal part, we have the following, like we would like to connect this expression that you have seen here already quite a few times, namely omega 1 free and omega 2 free. These are like exactly the coefficients that you get from the shape operator. So let's try to see the connection. if you have the shape operator at the point C of t and we plug in the vector field C dot of t, then by definition of the shape operator or definition of the omegas 1, 3, this one will be we have to plug in C dot of t in omega 1, 3, and then we get E1 C of t again, and we have to plug in C of t in omega 2, 3, and we get E2 of C of t. So that's nice because these ones are exactly the same kind of expressions as what we seen over there, except that over here we had them decorated by F1 of t and F2 of t instead of E1 and E2. But that's also quite convenient because we can take the inner product of that with that expression. With x of t. And F1 was then just like, we get like this term gets multiplied with the E1 part of x of t, which by definition was just F1. So what we get is that it's F1 omega of 3 C of t plus F2 of t omega 2, 3 C of t. So this is the normal part equals the normal part of ddt x of t. And over here we can like rewrite that a little bit nicer in terms of the second fundamental form, because that was the definition of the second fundamental form is if you have the shape operator dot product with a vector, what this is, we just take the vector that we have in the front, plug it in the first fundamental form in the first slot, and then the vector that you the inner product with goes into the second form. And for completeness, we do that all at the point C of t. So now if you go back to this formula, what we can write in summary, if you take all of these formulas, then what we get is that the tangent part was these two expressions. For that we introduced the notion of covariant derivative, and then we get the normal part, which is this expression. For the things in bracket, we just calculated that this one is the second fundamental form at C of t in C dot of t times x of t direction. And then we can write E3, but E3 is the same thing as the normal. So it's the normal at the point C of t. So that's the upshot of our discussion, is that we can combine this formula. The first term was the covariant, and the second one, by comparing over there, we got that it's the second fundamental form. And this formula is called the Gauss-Weingarten formula. So that's the formula that decomposes ddt of x of t into something that is tangent to s. So this one here is tangent to s. And that's again a nice vector field. And this expression over here, we see here it's normal to s. And yeah, so that's the upshot, is that we can calculate the tangent part and the normal part. One upshot, which is, yeah, maybe we can record some formulas that mostly follow from this Weingarten formula about the covariant derivative. So the perspective here is that we had this covariant derivative was defined by these two formulas, but they're relatively, yeah, sometimes they're nice, but relatively hard to organize if you want to some properties of the covariant derivative. But this formula over here allows us to say, okay, we can have some properties of this covariant derivative if you know the same properties for the normal derivative. And we can analyze what happens to this part. So it's a nice trick that we can use to study the covariant derivative. And what we get here is the following. Or maybe it's good to do that after the break, then you're well rested for the proof of the effects as well. So let's take a 15-minute break. So 25. We continue. Yeah, so I don't know. Like last year, it was also always activated, but I'm not sure if it's actually that more helpful. Like the idea is that you see it a little bit more in big, what I write, but I'm not sure if it's like really that more readable. There? Do someone wants to?
Video.
Good. Yes, but I still have to clean that one anyway, right? The idea is good, but
Maybe you should press E for seconds.
yeah. Okay, let's continue with the properties of the covariant derivative, and let's try our new tool, see if it helps. So the first result is that, the first result is that ddt of x of t, okay, yeah, whatever, that this one does not depend on the frame used in the definition. So we call like ddt of x of t was defined as the taking a frame, decomposing x of with respect to that frame, and then calculating ddt by this formula. So a priori it depends on the frame. But if you now look at this formula over here, you see that this side clearly does not depend on the frame, and this side here also does not depend on the frame. So ddt of like the covariant derivative also cannot depend on the frame. The second property is that we have ddt, and then we scale lambda, then we get a chain rule property, which is so that's the Leibniz property. And so for lambda being some map from the interval to R, and then we have for every smooth function, which is like a change of time essentially. So we have j of r. It's also an interval. Then we have dds of the chain rule. So this one is the covariant derivative along the curve where we take the c and precompose that with phi of x precomposed with phi in S is the same as having phi dot on S and then taking the covariant derivative of x at the point phi of S. So it's a very similar formula that you get for like the chain rule. If that would be just a normal time derivative, you would see that directly. So it's like a chain rule. And then we have some property that comes from the compatibility with the first fundamental form. So it's not the interval. So it's the first fundamental form, which says that for every xy vector fields along C, we have the following property, namely that if you take the inner product of x and y, you get a function that depends only on t. And if you take the derivative with respect of that function, so yeah, maybe. So you have x and you have y. You plug them in the first fundamental form. You get a function that depends on t. You take the derivative with respect to t of that function, and the formula tells you that this one is the same as essentially bringing ddt inside and first taking the covariant derivative with respect to f, and then plus the second term where we take the covariant derivative of y. So that's some kind of compatibility condition. And then we have a fifth property, which says that if you have a curve of that depends on a parameter, say from -1 to 1, be a smooth map. So that's essentially you can think of that as like some kind of rectangular, and that ddt be the covariant derivative along the curve where we take t and then map it to a ct of epsilon, where epsilon is fixed, and that dd epsilon be the covariant derivative along the curve where we fix t. Then we have the following equation, which says that if you first take the covariant derivative with respect to t, first you take the partial derivative with respect to epsilon of c of t and epsilon. So you consider c of t as like a family of curves, and then you take the derivative of the curve in the direction of the parameter that defines the variation. Then you get a vector, and you can take that vector, the covariant derivative, and this one is the same thing as just interchanging the derivatives. And this property is called torsion freeness. So the idea here is that we have one curve, and then we have a whole family of curves actually, which and in some way, like the epsilon says like in which curve you are. So the epsilon changes the curve, and the time direction here that tells you how long you are on that curve. So that's the picture that you should have of this C of t. It's like you can think of that as a family of curves. And then it doesn't matter if you first take the derivative in t direction, which is a vector that is tangent to a given curve, and then you take the covariant derivative in this direction, or if you first take the partial derivative in this direction, which will be a vector field along, say, like the white curve, and then you take the covariant derivative of that vector field. So that's the properties that we need. So the proof of the first three is actually very simple, and I'll let them essentially they follow directly from the Weingarten formula. Formula and for 2 and 3, and from the formulas from the chain rule and Leibniz and chain rule of the normal ddt of x of t. So you just take like both sides of this Weingarten formula that we still have up here. For that formula, we want properties of this guy, the covariant derivative. So what you do is like you take the same properties that you need for the left-hand side, it's ddt x of t, and then you just see that usually at the second part, the normal derivative just doesn't contribute anything, or at least not anything that is like difficult. So you just essentially want to verify like these properties, just write in this formula up here, like say lambda times x, evaluate both sides, and then you get the formula that you want. So that's pretty straightforward. So for 4.4, we just calculate the left-hand side. So we want ddt of x of t times y of t. So that's so we just use the normal formula for where we just plug it in both terms, and then we get two summands. So we have ddt x of t times y of t plus x of t plus ddt y of t. And now we use the Gauss-Weingarten formula, which is again up there. So we, instead of ddt of x of t, we can write this one as something that is tangent to s, and then something normal to s. But the normal part will be in a product with something that is tangent. So these normal parts will just not contribute anything. So this directly allows us to just replace here the covariant derivative. So here, so also again, the Gauss Weingarten formula using the fact that the second fundamental form terms blah 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 times is proportional to n, and then you take inner product with x of t equals 0. because this one is normal and this one is tangent. And essentially the same kind of trick also works for proving a second property. So 4.5. So we know that the second derivatives commute. So let's start in the middle. Here you have d dt of the epsilon of a curve. It's the same thing as dd epsilon dt of the curve. So that that's just like something that you know from your calculus course. So now we use that we know this dd epsilon we can replace by the covariant derivative plus something normal. So I can write this using the Gauss-Weingarten map as this expression plus second fundamental form evaluated at dd epsilon of the curve times ddt of the curve and then the normal direction. And similarly here, by just using the Weingarten formula, but now for ddt, we can write this one as covariant derivative of ddt of dc of the epsilon plus the second fundamental form evaluated at dc of respect to t and dc with respect to epsilon. And then again, there's a normal vector. And now the nice part is that the second fundamental form was symmetric, that we had like shown at some point. So we can change the arguments and we get the same result. So you see now that this term here and this one term here, they just cancel. So normal contribution cancel since second fundamental form is symmetric. And what you end up with is exactly this formula that I claimed here, is that, the covariant derivative of the partial differential commute. Good. So that finishes the proof. One small remark in that direction. These properties that we are just shown properties axiomatically characterize the covariant derivative. So if you say like I could have defined the covariant derivative as the unique operation that has these kind of properties. So it's like in some way these properties uniquely characterize the covariant derivative. Okay, so that's nice, but actually not what we were, like these covariant derivatives and stuff, that was not what we were setting out to actually show and discuss. What we wanted to, from the beginning, was actually discuss what is like meaning for a curve to be a, or two vectors to be a parallel. So let's return to that question. So let's see, be a curve, like say, or maybe directly write the field.